Hello and welcome to a short video where I'm going to run through the process for running a forced vibration simulation on this ruler part. So as before, I think the first thing I'm going to do is I'm going to set up a little sensor on the front of this part so that we can use that to track the motion of the system. Set up a sensor. What I'm going to do is first create a point, I think, on the center of this face here. So I go to reference geometry and create a point at the center of a face. So at the center of this face here, it creates a little point. Point 1. So what I can do now is create a sensor or add a sensor here. And the type of sensor will be simulation data. And the data quantity will be a workflow sensitive sensor. So if we're measuring stress, it'll measure the stress at that point, or if we're measuring displacement, it'll measure displacement at that point. And sorry, in the blue box here, I want to select that point 1. Okay, so we'll be able to track the response of the system at that point with that sensor. Okay, I've previously run a frequency analysis on this part. I think we've seen this before, but just to recall, the modes of vibration of this beam. It's a cantilever beam fixed at one end. The modes of vibration, the first mode is here at 13.2 hertz. Second bending mode is here at 82.7 hertz. Third mode is at 231 hertz. The fourth mode is a torsional mode at 257 hertz, and the fifth mode here is at 324 hertz, and it's oscillating sideways in the Z direction. Okay, so what I want to do is I want to set up a forced vibration analysis where I could say what would happen to this structure if I applied a force at a range of different frequencies. How would the system respond? So I'm going to create a new study. The type of study is a linear dynamic study, and we've previously seen the modal time history option here. I'm going to do the next one here, which is a harmonic force being applied to the system. Okay, so linear dynamic study with a harmonic forcing function. And click OK. The first thing I want to look at is the study properties. If I right click and go to properties here, by default, it's going to model the first 15 natural frequencies of the system. So I'm going to reduce that down a little bit. I'm going to reduce that down to the first 5 natural frequencies, which we just looked at there, which was up to about 300 and something hertz. If I go to harmonic options here, by default, it'll look at the first 5 natural frequencies or up to 100,000 hertz, whichever comes first, I believe. So I'm going to reduce that down to about 500 hertz. I think the last frequency that we looked at was 350 or something like that. So I could maybe go down to 400 hertz even here. We'll have a quick look at the advanced options. So what the system will do is it'll look at the first number of frequencies. We've told it to look at the first 5 frequencies. It'll create a series of simulation studies clustered around those natural frequencies. And you'll see that when we look at the response graph later. By default here, it's going to do 15 data points or 15 studies clustered around each one of those natural frequencies. To reduce the time, I'm going to reduce that down to 10 studies for each frequency. And I'll leave the interpolation on logarithmic, and I'll show you what that means in a few minutes. And I'm going to leave the bandwidth as it is as well. Okay. So to set up the study, then we want to apply a fixture. So I'm just going to use a simple fixed geometry fixture, as in the previous study. So if I right-click and go fixed geometry, I'm going to fix this split line area down here. And we want to apply a force. And I think what I'll do is, in this case, I'm just going to apply a vertical downwards force to this area here, the cylindrical area of the hole. So I'll apply a force to that area and pick a direction of, in the pink box here, I'm going to pick a direction that's perpendicular to the top plane. So normal to plane. And I'm just going to apply a small amount of force. I can't remember what we applied in the previous one, so I'll just say 2 newtons or something quite small. It's a very low stiffness beam. So we'll apply a small amount of force, and that will be the magnitude of the force. Now, how this differs from a static simulation or previous studies that we've looked at is this value here. And it doesn't really indicate it clearly in SolidWorks, but what this is an amplitude of force. So effectively, we're going to be applying a force of plus or minus 2 newtons as a sinusoidally varying force. So it'll be F sine omega t, where F is the 2 newtons, the magnitude or the amplitude of that force. Okay, we can, if you have multiple forces, you can set them up in different phases to each other. So it would be the sine of omega t plus phi, and you can put in your phi angle here in degrees or radians. As it is, I'm going to leave that as 2 newtons amplitude, and we're going to run this study at a whole range of different frequencies from 0 hertz up to 400 hertz. Okay. Yeah, just to be aware of that, that's the amplitude of the force, and it'll be running it at a number of different frequencies. If, for example, you wanted to model a out of balance centrifugal force where the magnitude of the force increases with the frequency, you can set that up in here. You can create a curve for how the amplitude or the magnitude of that force increases with frequency. I'm just going to be applying this as a constant magnitude, a constant amplitude force of 2 newtons times the sine of omega t. So we'll leave that on constant. I might swap the direction of it. It won't really matter. As I said, it's plus or minus 2 newtons, but just I'll swap the direction of that around. Like so. Okay, next thing, I'm going to create a mesh for that. I'm just going to use a fairly standard mesh, but what I will do is I'm going to make it fairly coarse. I'm going to reduce the mesh density or increase the element size here. I have a fairly coarse mesh, which should hopefully reduce the time it takes to run the simulation. So I've got about 2,000 elements and about 5,000 nodes. And lastly here, then we need to include material damping. So if you had no damping in the system, you'd wind up getting infinite resonance. So obviously we don't want that. And in fact, the simulation just won't run if you don't have any damping. So I'm going to set the damping ratio to 0.05. And OK. And that should be ready to run now. Option I want to just look at before I run the study, though, is if you go to results options, right click on results options. I just want to set it so that it'll track the my sensor that I set up earlier. So I can set it to all track data sensors, or in this case, because I only have one, I can set it to workflow sensitive 1 either. Okay, so when I run it now, it'll take a little while to run the simulation, because effectively it's going to run 10 or 15 different simulations for each natural frequency that it's calculating. I've set it to calculate for the first 5 natural frequencies and 10 data points for each, so it'll need to run approximately 50 simulations, a little bit more because it does some at the very low end of the frequency range and the very high end of the frequency range as well. So I'll just set that to run, and I might pause the video then and come back in a couple of minutes. You'll see here it's doing 61 steps, and it's running through them fairly quickly because it's a fairly coarse mesh. But this type of study can take quite a while to run. So I might pause the video and come back in a few minutes. Now, it actually ran through it ran through the simulation quite quickly. As I said, it was 61 time steps, roughly equivalent to 5 natural frequencies with 10 data points for each, plus some more some more data points at the very start and the very end of the frequency range. It's not unusual for this type of study to take, tens of minutes to run, maybe half an hour, maybe an hour, depending on the complexity of the model and how many elements you have in there. This is a very simple model with very few elements, so it didn't take too long. Okay, so we can have a look at the results plots. By default, it gives us a von Mises stress plot and a displacement plot. What we're actually looking at here in this particular study is plot step number 61, the very last step, which is happening at 400 hertz. So this would be the response of the system if you applied the force at 200 hertz. You can go back individually through the plot steps. Individually, they don't really give you a whole lot of information unless you're particularly curious about a particular plot step or a particular frequency. So what's more useful is to view all of those results plotted out in a single graph. So you can go to your results in the feature tree down here and define a response graph. So we can define a response graph for any node at all in the system, but because we have a sensor set up here already, I can pick the response, say for the stress or displacement at location 3075, which is 0.1 that I defined earlier on as a sensor. So what I want to do is I want to look at the displacement of that point number 1, on the y-axis, and on the x-axis I'm going to have frequency in hertz. And it'll do it for the full range of frequencies from effectively 0 hertz up to 400 hertz. If I click OK, that gives me the response of the system here. So you'll see that at 0 hertz, which would be similar to doing a static simulation, the ruler will move about 22 millimeters at the tip. So if you applied a force of plus or minus 2 newtons very, very slowly, the ruler would move plus or minus 22 or 23 millimeters. If you applied that force a little bit faster, so at about 7 hertz, it would be going plus or minus 40. If you applied your force 2 newtons at plus or minus 2 newtons at 11 hertz, the system would be moving plus or minus 80 millimeters. And around about the first natural frequency, so at about 13.7 hertz, the ruler would actually be moving plus or minus 228 millimeters. Okay, so you see this big spike around about the first natural frequency here. Part of that is because the ruler, in its first mode of vibration, the tip of it moves a lot anyway. But also then you're getting resonance around about that first natural frequency. This second peak here corresponds to the second natural frequency of the system. So at around about 82.3 hertz, you're getting plus or minus 6 millimeters movement of the system. So this is the amplitude of the displacement response of the system. Okay, there's another very small peak here around about 240 hertz, but it's not, the movement is so small that it's kind of hard to see. Okay, so that's those values plotted out in the default visualizer within Solidworks, but you can also save those values as a comma separated value file here. I might do that off camera, and I'll just come back and talk about that briefly. So I've exported the results in that response graph. I've exported them to a comma separated value file, and what I've done then is to just plot out those data points. So it literally gives you a list of values for your x coordinates and your y coordinates. And I've plotted out those values just on a simple scatter graph with no smoothing lines between. And it just kind of demonstrates the clustering of the data points around about the natural frequencies. The first one here is kind of hard to see because it's such a high peak. The second one is maybe more noticeable. You can see you have should be about 10 data points clustered around about the second natural frequency of the system. You have another cluster of data points around the third natural frequency, fourth natural frequency, or maybe that's the third and the fourth and the fifth. And then you have another cluster around about the 400 hertz around the top of the range that we set earlier. Okay, and those each of those data points are clustered kind of logarithmically, so the points are more concentrated right at the natural frequency point. That was the option we set up in the study properties, to have them have 10 data points per natural frequency and have them logarithmically distributed. You see there is a point in here between each of the natural frequencies as well. Okay, I'll pause it again for a second. This is our response graph for the displacement of our sensor here, point number 1. We could also, for example, we could do a response graph for different quantities such as stress. Now the stress at the free end of the cantilever beam will be effectively 0, so I'm going to pick the stress at a different location. I'll define a response graph for the stress somewhere back here close to the fixed end, let's say this node here. So I can use my predefined location, my sensor, or I can choose from a list of all the nodes in the part, or I can select one from the mesh of elements here. So I've chosen node number 133, and I can pick, I can draw a response graph for the stress, displacement, velocity, or acceleration at that location. So I'm going to pick the stress. Von Mises stress is fine as well. So if I click OK, we can see the stress at that end of the beam. At very low frequencies, we're getting, what's that? That's about 101 megapascals. At very, very high frequencies, or sorry, at frequencies close to the first natural frequency, you get very high stress there. So that's actually coming in 1.1 gigapascal. So that would be probably enough to break the ruler at that frequency. Okay, so that's the response graph for the stress at a particular location there. So I think that kind of covers everything I wanted to look at for this. It's a forced vibration response of the ruler under a harmonically varying force here. So even though the magnitude of the force is very small at 2 newtons, depending on the frequency with which you apply that force, you get very different results, stress or displacement. Okay, I'm going to stop the video at that, and thanks for watching.